So if you look at section 41, which is what this is, this section really, this study group is supposed to be based on around, you'll notice that they're relatively short. And like I said, I feel like it's because neural networks, like, it sounds very intimidating, and like the mathematics is pretty intimidating, but once you understand the mathematics, it's actually pretty interesting, like how simple it is to implement. The point though is saying, like, how do you implement it and make sure, how do you make it more efficient? So one thing we use basically is with, well, one common package basically is Keras. So right here is just Keras, what's it called? Their home web page basically. And so Keras basically allows you to build neural networks, specifically, deep neural networks. Deep neural networks basically just mean many, many layers. So if you think back, like here, a deep neural network this could be considered a deep neural network. And this is kind of like the big, state of the art kind of stuff right now of saying, how do you apply a deep neural network in different ways and stuff like that. And there's different, like, adjustments and things you can do. But basically Keras allows you to build these networks with basically like a really simple API. It also allows you to think about all the stuff where you would have to like figure out how to computationally compute it. For example, when we make efficiencies, do you do the computation on the CPU, the GPU? How do you do the GPU? Can you do it in parallel? Like, so basically allow it to compute faster. Like all these extra things that you, like, if you had to go way into like the code and stuff and dig around, it quite honestly can be, I mean, there are people who do this kind of stuff, but for data scientists, it would just be a whole other thing to have to deal with on top of actually getting a product, basically doing a prediction model to move forward. So Keras is really nice, is that it actually, what's it called? It allows you to build things relatively quickly and easily. And what's interesting, you'll hear like fast prototyping. Basically, this allows you to say, all right, like I said, the big part of like neural networks is not necessarily, what's it called? Like, I mean, there's parts like, saying what's the learning rate, what's the activation function, all these things. But a big part of it is just figuring out what the structure is going to look like. So this allows you to very quickly like prototype it. And then basically you can use tools to actually export this out into, what's it called? Into production level code. Basically, really deep level like C code, so you can basically put it in any system you want or make it much more efficient, much faster. So that's what some of the reasons we have this. You'll notice here it says about TensorFlow. TensorFlow is one of the more popular libraries basically for neural networks, machine learning. I think I showed you the playground.tensorflow. They're the ones who built this. This is the one that's an open source from Google ML. Note that there are other packages too. For example, besides just Keras, there is something called PyTorch. And PyTorch, oops. Sorry. PyTorch has another kind of structure doing it. Basically the same idea where you don't have to think of all the stuff yourself. So let's see here. So I kind of like, if you actually go to their website, keras.io, they actually show a really quick, like, how to build a model. And so I kind of have that put together for us right now, just to kind of show you. And just to kind of show you like how this would actually work and everything like that. But simple as this, you have import Keras. So make sure you install this through Anaconda if it's not installed in the environment already. Okay, so I'm just going to import that, right? So note that I had to also connect it to, in this case, I have it connected already to TensorFlow. I installed it. You don't necessarily have to have it. It's just that that's why I had it pre-installed on, or not pre-installed, but pre-set up on. And you can see we have our sklearn. In this case, what I'm doing here is essentially I'm just doing our standard stuff that we've been doing for other ML stuff, which in this case, I'm just getting just a random data set. In this case, the iris data set, which is really small. Like it's only got like 150, I think, data points. But I just wanted to show you an example of what you do. So this right here, this is like all of the stuff we normally do. We load in our data. We get basically what our different features are. We hit our target. You can see here, basically, I'm just getting the names, feature names, which is not super important because we're just doing it one hot encoding, right? And then we have the scalar. We don't necessarily have to do this, but this is actually, I don't remember where I got this code. I think I just borrowed this code basically and just said, all right, let me just get something to load in a data set. And you can see I get my X train, my X test, my Y train, and Y test, right? So we can actually train our model and then we can test it afterwards. So this is like nothing unusual. And we could have put whatever data set we want here, okay? Actually don't need this part, but That's fine. So then right here, we can see for Keras, we can actually import models, layers, optimizers. We can actually basically say, okay, what kind of model we're going to use. In this case, we only learned about something sequential models, which are basically just these guys. Sequential meaning that you're just feeding it forward through it. There's other types of models, which we'll talk about, like RNNs, recurrent neural networks. And basically they're built around neural networks, but they basically allow you to have some time dependence in a way, and they're really useful for like natural language processing. But you know, in this case, we're just looking at sequential. So for the most part, for neural networks, you would basically have import this sequential. So let me go ahead and import these models. Our layers are basically what kind of thing we have. So one part that I didn't really mention about is like each part is like our little like these are usually called like our layer right here. Keras calls it like a dense layer. So basically like how many different like units you have in here. At the very end here, we also need a softmax. Basically our softmax function allows us to say, is it going, you know, is it a 3, is it a 2, is it a 1, you know, depending on whatever the inputs are from this layer over here. So that's what it means by layers when we're talking about for Keras. And then optimizers basically allows us to do other things. We can talk about that another day. But for example, there's like the atom optimizer, but there's a bunch of different optimizers you can do. You can build your own, for example. So we import this guy. We're going to basically build a model. We're going to make a sequential model, which basically means a neural network that we've seen so far. Okay, so you can see here, like so far, like there's not too much code that I had to really deal with. And so this guy right here, I'm importing layers. So I could have put this up further, but I think this is more or less from actual keras.io. So basically I have our layers. I'm importing a dense layer, which is basically going to be our network that looks like this. Okay, this is our layer that we're making. So in this case, I'm actually making an activation of 4 layers right here. I'm going to start off with 4. Our input dim is 4. And the reason why I only know that is because I can, if I actually checked out, let's see here, what's X? So if I look at X, you can see here is basically we have 4 different features. So that's why my input right here, oops, our input dimension is 4. Basically, I'm only putting in 4 features. If I had 5 features, I had 500 features, this would be 500. So it just all depends on like what your input dimensions are. Okay. Obviously, the more dimensions you have, basically, sorry, for each feature, that means you're going to have one of these. So you can see I have 4 basically nodes right here for the input layer. So that's what it's saying. So okay, input is 4, and then we're going to output 4. I could have changed this, for example, let's say I change it to like 6, just like something. So that basically would be similar to if I had 4 here, I would go to the first layer is 6 different nodes. So that's what I'm building right here. And then I'm actually just going to build 1 layer. So this is essentially like our input layer, which is 4 of them, right? And then our next layer, which is 6 of them. And then we're going to output into 3 units. And the reason why I do 3 units is basically it can either be 0, 1, or 2 as the different labels in this data set. If you had like the number of digits, like handwritten digits, 0, 1, 2, all the way through 9, your units would be 10. So that means like the output basically would have 10. And you can see here, I have the softmax function basically saying which one's going to be the one that we actually classify it as. Like we're basically squishing everything down. And again, you can see the activation, I just used ReLU. Okay. So essentially what this will look like, if I were to draw this out, and I'll just quickly kind of annotate this out. If I draw this exact thing out, basically I have my inputs, which is 1, 2, 3, 4, which are all these, like basically you can think this is one data set. I'm going to input these in, okay? And then I would have 6 nodes here. And then at the end, I would have 3 different parts. So you can see here, and if I were to connect all of these, like it would be a pain if I did all of it, but you could get to that point. Like basically all of these parts would get here, they would all connect over. Basically this is my input layer, my hidden layer, and then this is my output layer right here, okay? So that's what this function is right here. If I instead were to put another, like if I were to uncomment this out, let's say I put input units of like, I don't know, let's say 4, then I would just have 4 right here. Okay, and it would all connect to here and then connect to here. So you can build complexity. So the more complex you have, basically, the more likely you're actually able to describe the mapping of your classification from your inputs to your outputs, but it takes more time. So that's kind of like the trade-off you do. In this case, this is just a small data set. I don't even think I need high complexity, but I can kind of show you. So we have our 6 units here. So our really simple network, okay, you can see here basically it's just letting us know, it's like, okay, it's all put together. Yeah, it's just letting me know, hey, some of these things are outdated. That's just for my internal stuff. Don't worry about that. And then we have right here a model compile. So what's really interesting is that Keras basically builds this model from object-oriented programming and says, okay, once you have this model, then what it does, it basically not optimizes it, but like it compiles it into machine learning code, which basically allows the machine learning. This is the layer where we won't have to like go deep into the C code and like the byte code or bit code or machine code itself, and actually be able to say, all right, you're going to do this exact thing for me, and you're going to make all these efficiencies. Basically, this model.compile allows us just to do it for us, so we don't have to like think about it. So basically, we're telling its loss function. It's like, how are you going to calculate loss? Because remember, loss can be a lot of different ways. In this case, we're just going to use categorical cross entropy. So we talked about cross entropy before, I think. Basically, this loss function can be any function you want. But in this case, I've defined it with this function that's built into Keras already. An optimizer, sometimes people will use like the Atom optimizer, but here just to, this again was just directly from Keras.io. This is basically use stochastic gradient descent. So we'll talk about stochastic maybe, I think next time. But basically, just know that basically we're doing gradient descent with a learning rate of 0.01. We have momentum, basically. You can think of momentum as essentially allowing you to kind of like, if you like go down a hill, like if you're going down a hill, you kind of want to keep going to make sure you don't like accidentally like stay in a local minimum. So if you imagine like, I should just draw, I always should just draw in here. I don't know why I always defaults to this ugly green. So if you have like your function and you have like a little minimum right here, but then you have your big global minimum right here, if your learning rate is too small, right, it'll stay at this point here and never reach out. So this momentum basically allows it to basically, like you imagine like rolling a ball down the hill. It doesn't just like go down the hill. It also kind of allows you to kind of go up and see, hey, is there something over above? So you basically allow it to some extra like momentum to allow it to check over to see if it can get into a new global minimum. So that's what this part is right here. And then Mr. Evolve, you don't have to really worry about that. That was optional. So basically we compile this now. So basically this is converting it all into machine learnable code. So it's really nice and easy to go through everything. Then what we do our model.fit. So notice that we already did the X train up here, right? We already split that X train and X test. In this case, we have about 40% left in the test size. I did 40% just because what's it called? The data set's really small. It's only 150 data points, but that's fine. But we'll have our X train, our Y train, our epochs, and our batch size. So X train and Y train, that kind of makes sense. Basically, these are our classification parts. Our X train will basically what we pass to the model. The Y train will allow us to calculate our loss and basically ultimately our cost function. And then we do that. And then we would basically back propagate it through, basically readjusting all the like the weights and the biases together. And then we pass it again through. So basically passing it through once and then going backwards is one epoch, right? One epoch. And so we basically will just do this, 10 times going back and forth, back and forth, back and forth. The batch size, if you remember, is basically saying how much of the data we'll actually use to, how much of the data we'll actually use to pass through our model. Okay, so this batch size right here is basically defining like how much of the data we want. If we had, in this case, we could probably pass the whole batch, and the whole batch is basically all the training data because it's so small. But if you had a very large data set, for example, if you had a data set that was like, for your training size, let's say 500,000, well, that's a huge amount to pass through every single time to the epoch. So you might only use a portion of that with the batch size. And you can do that multiple times. So one thing you trade off for, well, you make a small batch size, so you can make it go, your epochs will go really, really quick. However, if it's, if your batch size is small like that, you still have to go through more of epochs, basic epoch. I call them epochs, but like you have to go through more epochs to get through more of the data. So if you have a batch size of 16, but you have 500,000 and you only do 10 epochs, well, you didn't go through all the data. So you have to basically increase its epochs, but your epochs will go very quickly. If you have a larger batch size to the point where it's the same size of your data set, then what will happen is that the amount of time it basically goes through one training, feed forward, and then one back propagation will take a lot longer because there's a lot more data points to put in. So this is where basically the trade-off between epochs and batch size, you have to kind of figure this part out. In this case, it probably doesn't really matter because the data is so ridiculously small. So I don't even know how well we'll be able to get it. So you can see here, oh, you kind of, if you blink, you missed it. If you did, basically the model.fit allows you to basically go with these parts. And so in other, if you have a very large data set, if I had a very huge like batch size or much more complicated, this will actually take some time for actually go through. But basically each epoch, right, basically tells you what the loss is. So like it basically passed through it once and says the loss was 1.1064, because remember we want our loss to go as small as possible. So basically once it goes through, it's like, okay, your loss was 1.1064. And so it back propagates that loss, right? And basically readjusts the weights and the biases and then passes forward again and then says, okay, your loss is this one, which really makes sense. We're getting a better loss. When you start getting to, I don't know if this will actually reach this point. Let me see if, well, we'll try this. But one thing you can do, it will do each epoch and show you. When you sometimes get to a point where your epoch is like here, but your loss function like either is not changing or fluctuates up and down, up and down, up and down, you're basically at this local minimum and you haven't reached the, well, you either reach the global minimum or you reach the local minimum. Basically, it's stuck at that little point, basically going back and forth, back and forth. So this is one of the things, like you can kind of see like how it decreases very quickly, and then it starts slowing down how much it actually decreases. That's pretty typical for what you would expect for when you're doing gradient descent. So we completed 10 epochs, basically went through forward and backwards 10 times using 16 data points each time. Okay. This one right here, Keras mentions that you can basically do this by hand. So you can basically just train on a specific batch on each part. So I just kind of skipped this, but it's something you can basically specify. And then right here, we actually have this model.evaluate. So we have this model, it's now fit with the data. So this model now encompasses this basically the right weights and biases according to this loss function and everything. So we can actually evaluate, say, okay, well, how good was our model? And you say, okay, let's do the X test, Y test. You can specify batch size to say like how much of the data you actually want to care to like do a quick loss metric. And you can see here, it's like, okay, we got about 0.398, which is pretty close to our actual loss here for their training. So remember, this is from the test. This is data that is never seen, it's never trained on. I think I could also get rid of this batch part. And you can see here it changes to the whole data and still pretty close to the same size. So that's because I don't even know, let's see here, if we can, let's see how big y-test is. See, y-test is pretty small. It's not that big. What's that? Probably like 30? Oh, 60. Yeah, okay. It's still pretty small. Okay, so but the point is basically like, okay, we passed this whole thing. Its loss basically is about 0.34. So like, okay, that's pretty good. So now we can actually say the classes. So we can actually use our classes here, model.predict, basically say, okay, from X tests. So the stuff that is never seen before, I don't know, I have this batch size 128. I don't need this. If you only want to test a small portion of the testing data, you can do this. In this case, we're just gonna have 60. So I don't know why I have batch size 128. But basically say, okay, take these points that's never seen before for X tests and say, what are the actual, what's it called? What the actual, I'm losing my train of thought. What the actual labels are. So basically have our classes here. Basically it should be either 0, 1, or 2. So I have my predictions, and I'll show you what predictions look like too. Oops. You can see here basically is that what I'm doing with this argmax is if I looked at, let's say, just classes. Oh, that's all right. I need to clean out my keyboard. So you can see here basically it's that it's saying, okay, I think it's 96% chance that it's this one, a 0. It's like, oh, it's a 90% chance it's a 0 here. In this case, it's, oh, I think it's a 52% chance that it's a 2. So this is what I'm doing basically. These are the predictions. You say it's a 0, 1, or 2. Okay. And when I do predictions.np.argmax, basically I'm just saying what position is the maximum. So when I do classes, say, okay, well, in this case, this is the biggest one, so put out a 0. So you can see the second one's 0, the first one's 0, the second one, or the third one is 2. Basically just find the max argument, which is what we really care about. Say like, you know, how, like, of the actual labels, which ones works, right? And this is gonna be different from the loss function, because remember the loss function is comparing this to, like, let's say this is the actual one is 1, or actual one is 0. It's doing 1 minus 0.96, but it's also doing 0 minus 0.02. and 0 minus 0.01 and adding up those squares, basically. That's our loss function right now for a categorical. Oh, I said, sorry, it's not squared because it's using categorical cross entropy. But basically, it's using all of these values. In this case, I just want to say, did it predict it the correct one, right? So this loss function might be different. Where is it? This loss right here, which is of the whole part, will be different from how well I do accuracy-wise. So in this case, that's what I'm going to do. I got my predictions, and now I want to see, okay, when is predictions equal to the actual value of y-test? And remember, I think we saw y-test in a second ago. But if you see y-test here, you can see basically it's 1, 1, 0. So you can see the first three we actually got right? But I don't want it to be like this. I actually want to say, hey, like, is it a 0, 1, or 2 for it? So I can say, okay, this is basically going to be a list of 0, 1s, and 2 for each data point. This is going to be a list of 0, 1, or 2 of predictions from each data point, and we're going to see how well did it work. And so we can see here, I did divide it by predictions to shape, so I can actually do like the fraction and say 88%. So 88% were correctly identified as what's it called? As the right label. So it's like, cool, awesome, right? It's like, well, 88%, we could probably get a little better. So kind of just going forward, and I'm gonna comment out some of these stuff so we don't have to keep seeing over and over again. And we can rerun this whole model or this whole test again. In this case, this test is, this model is pretty small. If we had a much larger model, it would take a lot longer to actually process it through. But I'll just quickly show you, is like, for example, I could either put in more epochs right here. So for example, let's say I do an epochs of like 100, okay? So we'll keep the same batch size. I'll just run the whole thing all over again, restart, clear output, and then let's go ahead and run all. So remember, we got like about 88%. So we see at the very bottom is training right now. And you can see, here it is. So you can see there's a lot more now. There's 100 different steps. You can see our loss function, our loss basically is very, very small compared to before. So we probably have about 100%. We get about 92%. I could also do things, for example, I could make this a little more complicated. For example, I can make this units, for example, let's do 16 here. Okay, so now I have 2 different layers. So let's go ahead and do this. I'm just doing a restart just to make sure I don't have anything funky that carries through. So I do a restart, and it's going to train for 100 epochs. And last time we got like 90, what was it, 92? So okay, 92. So this is about as close as we probably could get. We might be able to adjust it more. Like we can, for example, maybe try to change it for like 500 or something like that. But the point is basically is that we're probably reaching to the point where it's really, really close. Our loss function is really small. So there just might be a pure chance of just saying, you know, we just didn't get the right training data from a thing, but that's okay. And this is stuff you have to decide if it's worth it or not. You can see here, my computer is going pretty fast because it's a small training, so it just finished. And you see 92 still. It's like, okay, not the best, but it's all right. Like that's better than our 88. So you can see you can make more complexity, adjust things, you can change maybe your batch size or whatnot. Okay, so that's kind of essentially like, I just showed you essentially how to train like a neural network with Keras. And you can see it's not too bad to actually put this out. The hard part is actually trying to figure out like this structure right here, and then adjusting the hyperparameters, which are things like the learning rate, momentum, what optimizer do you use, what's your loss function going to be looking like, all this stuff. So any questions, Asad?
No, I think I got it. This like the whole Keras model kind of made a lot of sense.
Yeah. Yeah, it's like it's a godsend when if you do the lab for like when you do it like I like to say it's like a trial by not trial by fire, but basically like a rite of passage to like do back propagation and feed forward and neural network from scratch, and then you find out it's like really inefficient like in Python because you know Python's just not optimized to its level. Like you could do it all right with NumPy, but basically using a package like Keras, it's just like, oh, cool. Like just basically run it through. Everything. Yeah. And it's nice too that a lot of packages like TensorFlow actually have Keras built into it. So you can actually piggyback onto Keras and TensorFlow and allow you basically use those parts together. And it just makes these neural networks a lot easier to design. There's a lot more that we haven't like talked about, like different stuff. Like for example, I think not next time, but time after, so a couple days from now, we'll do convolutional neural networks, and that's more like for images. And this basically adds a little extra part to our neural network, but in the end, basically, we're still doing a neural network, and we're still designing it. And it just, you can basically, I think the complexity and the hardest part ends up being about designing this model itself. So something to look forward to. So cool. So that kind of ends. yeah, that kind of ends everything I was going to talk today. You have any other questions or anything?
No,
Um,
I think just going through the lab, I'll probably come up with any questions that I might have.
yeah, and kind of speaking to the lab in general, because the labs will kind of make you do it by hand. I think it's really important. It's not something you're going to do, like as a data scientist, but I think it's really important. It's kind of like when teachers make you do the math part, and you're like, "What? There's such an easier way to do this after you like learn the hard way." I think it kind of helps you want to appreciate how much is going on here, but also gives you an idea of like hopefully kind of helps solidify a little bit like what's going on when I'm writing this dense layer. Like the thing is like I could like have this copy and paste it or just literally type it out and not understand anything that's going on. It's like, oh, I need to adjust these numbers and something happens. This is why it's important to understand like, you know, the different parts and saying, okay, like these are the things that are going forward. And that's probably like the strongest, like I would say your like the advantage you have as learning data science, you know, being a data scientist is be able to say, hey, like I know how to adjust these things to make it more efficient or for the specific model or whatever. Or when you get something, it's like, wow, this model is really bad. You say, oh, it's like, oh, shoot, I had the learning rate set to 0.1. I'm like, oh, that's ridiculously big. Like that's way too big for this model. And you make it much smaller. Or it's like, oh, it's taking a long time. It's like, oh, I have it way too small for this learning rate. I need to adjust these parts or whatever you need to do. I think those are the parts that help a lot. So cool. All right, so I'll go ahead and stop sharing and I'll go ahead and stop recording.